No, 'cause it doesn't go full screen if it's not recording. Or it goes
Oh,
to full screen, but if
it
it's
goes
not-
to like just the notes if I'm not.
If you're recording,
Well, I can't tell because this screen never changes for me. So, I just wanted to go through this idea. We're going to call this 7A. We're going to say member releases. Because we're going to be doing that. When we start modeling things in VA, right? I'm going to show you a drawing set, and you're going to have to say model something, and in that drawing set, we're going to have shear tabs, and as you know from steel design, right? Shear tabs, we have a lot of times, very common to have, say, an HSS column, tube steel column. Okay. And on that column, we end up welding a shear tab. Maybe it's a 3-bolted shear tab connection. Maybe you have like a W16 or something like that. Then you end up with something that looks like that. Okay. In this case, these holes might be short slotted holes or long slotted holes, right? So there's the ability for this thing to rotate a little bit. We also, have you guys, are all of you in steel design, or some of you have already taken it?
Steel 2.
It's steel 2 right now?
Yeah.
So you guys talked about like the design of shear tabs, or was that steel 1?
I thought there was one.
We haven't collaborated, I don't think.
Okay. Well, there's like dimensional requirements in the steel manual that require you, like, you can't over design the shear tab. It's gotta be a certain thickness based on the welds and things like that, so that there's actual rotational ability for this connection. They wanna make sure that it doesn't act more than just a pin, right? Even though it's gonna act more than just a pin, right? We idealize it as that. So if we do that, yeah.
What do you mean there's can't over design?
There's requirements on like the thickness of the plate versus the.
Can't you just bump it up in the table?
Yeah, but so those table values, if you look in the steel manual, there's like underneath the shear tab
Yeah.
in the steel manual, it goes through all the connections, right?
Yeah.
Well, in there's some inequalities that the shear tab needs to meet with respect to thickness of the plate and weld sizes. Same with like, if you do a single angle connection, they assume that that angle can kind of pull away from the face of this column or supporting member to allow some of those rotations. Because if you made this like a 1-inch steel plate and welded the shit out of it, right? It's gonna become pretty stiff, and you did standard holes, and they wanna try and keep you from doing that. And so there's some inequality stuff in there. Which I thought was like a steel 2 thing, because I think when I was in steel 2, that's what we talked a lot about connections. A lot about connections. So anyway, so we assume, long story short, we're as structural engineers, there's a lot of times where we impose requirements on connections, right, based on their design, whether that's allowing, right, in this case, if we had long slotted holes and we did just snug tight connections, we might assume that this beam could move in and out as well, right? It's not gonna pull on this column. Or in this case, right, it might not rotate, and so, right, some connections may not transmit all of our forces, right? Some connections in this case, we're talking about our R1s and M1s, right?
You get into trouble then, if you have a lightly loaded section that's a little oversized, and you call it the same shear tab as you do with more heavily loaded.
I mean, you
section.
could if you were like really gnat's ass in it, but in I mean, you gotta kind of step back sometimes and squint. I mean, for the most part, as long as the tab meets the design requirements in the manual.
Yeah.
Like the other thing that they require you to do is like if you do extended shear tabs, now you gotta start taking into account the moment, right? That happens bolts. Because you want the moment to happen at the bolts and not the actual connection at the end. It's assumed to be pinned. So you're assuming that this shear tab at the end, when it's rotating, is doing some yielding going on. And so that's why there's requirements on the thickness of this shear tab and stuff. And so that's why, like, if you have a, I'm sure like in Hicks or DCI or TD&H, who else fucking works out there well? Oh yeah, is it Bridger, right? Yeah, your eccentricity of these bolts is probably 3 inches. If you look at your shear tab connection, right, and it's 3 inches anywhere, right, anyone you look at, and that's because at the code level, you go much more than that. You start taking into account eccentricity in these bolt connections. It's like a sweet spot.
3 inches. So in this case, for a shear tab, right, we're going to have approximately 0 moment transfer. So how does VA account for essentially letting go of the ability to carry force, right? We're not restraining it. We're not saying displacement 0. It can displace all at once, right? Now we're setting force is equal to 0, right? We're getting on the other side. So what we end up doing is if we look back, you can recall that on our local coordinates, I'm just going to stop there. We get this force displacement relationship, right? F equals KD. In this case, we had our axial tractions, our transverse uniform load, right? These were called our equivalent energy forces. And those were all equal to, right, stiffness times displacement.
When you step into VA and you say, all right, I want a simple connected member, and some of you have probably gone in there. We'll go through VA here in the next week or two, and we're gonna take a class period and just kind of walk through modeling and steps through doing it, and what's available, what's not available, how do you report things, how do you model things, what's important about modeling things, okay? When you step into VA, right, you have the ability to, at every node, provide some sort of fixity, right?
And in VA, this model might look like, if we looked at it in plan view, you might have, well, let's go back here. If we were looking at
the plan view of 3 beams framing into a column, okay? 3 beams framing into a column, right? This column's extending in and out of the page vertically.
if we had a shear tab,
Right? We know that that member, right, is not going to provide any moment transfer from that member or the forces that are acting on it, right, into this member,
into that column. And so VA denotes it by this little circle, and I'll show you guys that, right?
so you know what's released and what's not released, okay?
So when you do that, VA goes and says, okay, we can now partition our equation, right? Our elemental equation.
To separate things out with respect to what degrees of freedom have fixity and what degrees of freedom are unreleased,
right? Or sorry, released, right? Or no longer fixed. So we create. Today's the day you guys really respect me about giving you Spark or the skeleton notes, huh?
Oh, we appreciate that.
Yeah, do you? Don't feel appreciated some days, all right? So we end up moving, right? In this case, right? If we had a beam that was framing into it,
right? We're gonna have some degrees of freedom. We're gonna have U1, V1, right? And rotation at 1. So we have 3 degrees of freedom. So we have 6 degrees of freedom for this beam. Yes.
So that connection in that shear tab, like, it's made to allow rotation by yielding, like, they want it to yield.
Yeah,
so-
they'll end up, yeah. The way you
Like-
design it, you make it thin enough so that there's flexibility there, so that you don't get fixity.
Like, it's just like minor, you gotta just count on extremely minor rotations.
Yeah, I mean, you're talking at ultimate loads,
Yeah.
right? Where hopefully we never see those. Right? At service level, never know the difference. Not to mention, there's probably so much overstrength in the connection to begin with. I mean, the chances that you're actually, like a shear tab, it takes a lot of load for your standard shear tab connection, right? Some of you have probably gone through, like when I first started, that was some of the stuff I did at the end of a project. Is you'd go back through, take all of the readings in VA, and then you go through the table in the steel manual, right? And connect and make sure that there wasn't any connections that exceeded that demand in the table values, right? It doesn't happen very often. Like you have to have certain circumstances for that to happen. Usually you have way more capacity. So even in that sense, like even if you got to ultimate loads, you're gonna be far below the actual capacity of the connection. And so the chances of it even yielding at that point is probably pretty
So
slim.
does that mean that it is transferring?
Yeah, isn't that fucked up? That's what we assume. It's weird. We assume that it's pinned, but in reality, there is some fixity there. A lot of times in buildings, we do what's called slip critical connections, right? You guys are probably familiar with those, right? Whether in Damon's class or in practice, right? And we're essentially squeezing the connection so hard that there's enough normal force and a mu, right, a friction coefficient, that we're gonna be able to transmit a lot of force even if we didn't even have bolts in it, right? So then you end up doing that to all of these connections, and so now it's like, it's really a linear elastic thing where if you start pushing on the beam and you start rotating it, the friction forces are really gonna be transmitting some of those forces. And so they're trying to account for that by not making the shear tab too big, right? So that if there's one thing that is the softest element in the system, it's the tab and it can rotate. And so that it does overall behave like this pin member. There's a lot of things we do as engineers, and it's like, let's do it, it's worked. Right?
Sometimes.
Well, like at Hicks, you guys do a lot of stuff in the Yellowstone Club, right?
Yeah.
I mean, I've done houses up there. I mean, you could literally spend a year trying to figure out all of the combinations of drift loading that could happen on a house, right? So what do? You squint. You're like, oh, let's just kind of like put double here and something over here. Like that's really what it comes down. Have you guys seen that?
We've
Right?
got some snow load maps.
Yeah. See?
They're fun.
Yeah. It's a pain in the ass. You like have so many, and then you go up there and it kind of scares the shit out of you in the winter because there's some houses that have a fuckload of snow on them, like a lot of snow on them.
Not lately.
That's true. This year, yeah. Cross your fingers, right? Yeah. But we're designing for that 1 in 50 year sort of event. So yeah, I mean, we're as engineers, we are nerds in a sense that we like the details, but when we implement it, in some cases, you just kind of have to smear things out. Otherwise, nothing would ever get done.
Those houses are also way over designed anyway.
Yeah, I mean, there's a lot of redundancy that helps us in everything. Yes.
If you actually did design that as fixed, why don't they just leave it, like design the whole thing as if it's fixed?
Because then you definitely better make sure that it is fixed, and then it starts screwing up what's going on with the columns.
And it's just a lot more bolts and stuff.
Yeah, I mean, it's a lot more from a cost perspective to implement that sort of design too.
But you have to design for the amount of moment that's being transferred into that column, like at that point, it was like, is a moment transferred, you're saying there's no moment transferred.
Just assuming it's
Yeah, you
small.
assume it's zero.
You just assume zero, but it is like the service loads are transferred.
Yeah. So one thing like in like larger, like on the dining hall, for instance, right? Those are all pipe columns, and we have shear tabs going into them, right? In some cases, you'll see in that building, the shear tab, we ran completely through the column because we had certain conditions where the loading, so you gotta start thinking about like, as the beam sees it, there's zero moment transferred, as the tab sees it, zero moment transferred. But when you start looking at the eccentricity, you really have this beam that's landing on these 3 bolts. Well, now if you looked at a tube column, right, you have this knife edge that's trying to rotate. And so I would go through and look at, okay, what's going on, chapter K in the steel manual. tube shapes, right? You have to start considering the fact that you could shove the corner of this tab through the wall of this pipe or tube. And so you do consider things in some areas and not others, I guess.
Could you like assume that your moment connections are like carrying the concentrations of moments or anything along those
Explain that
lines?
further, James.
I don't know, just like stress concentrations, but with moments, is that a thing? Like, they just.
Well, I mean, like
stiffen
in
up
this
that-
case, yeah, I mean, you're gonna consider the eccentricity of the connection with respect to the wall of the column, right? But when you're designing the beam, you're assuming it's free to rotate.
Yeah.
Yeah. So the column you might sometimes look into like how much moment.
Yes. Yes.
Why do you
That-
look into it on the dining hall?
Why did we?
Yeah.
Because we had quite a bit of forces. We have like, if you go into the dining hall, there's big transfer girders and stuff like that carry like, there's a clear story when you walk in, you know, it goes up 2 stories.
How big is the pipe?
Some of them are like 12s, I think,
Oh,
10s and 12s. But also the big thing that happens when you start looking at lateral forces and you're starting to drag loads, like you like start looking at axial demands and collectors and cords, right? So now your brace frame might be like 3 or 4 bays down here, and you're trying to drag all that load out of the diaphragm. By the time you get to the 1 or 2 beams right before the brace frame, those loads can get pretty big. And so now you're trying to pull and push this shear tab into the wall of the column. I mean, you're really fucked. So you end up just, all right, I'm gonna put this shear tab through it. You gotta start looking at, okay, now you have this unbraced length of the column width, and that could buckle potentially, right? Or it could buckle, like I've had it some places where we had to beef this up or put plates on the top and bottom because just the unbraced length of 3 inches wasn't enough because we had like hundreds of kips trying to go through this.
Hundreds of tips of lateral?
Yeah.
Did you tell all that from a model?
Yeah, so you build a VA model.
Of
Right.
like just like one shear tab connection? Like you would make one big model and then each little connection?
I guess it depends on overall the structural systems used in the building, right? If this was a wood building and it had a steel frame lateral system in it, right? Then I would probably like look at it more from a by hand approach, right? Because you have flexible diaphragms, you can distribute loads really easily by hand and figure out like line loads that are going down your steel frames. If this was all steel frame and it had rigid diaphragms, big concrete diaphragms, and then stiffness really plays a role in where everything is going, then in that case, the model is the best approach because then VA is going to, or RAM or RISA is going to take into consideration the fact that your diaphragm changes depth, right? So the stiffness of your diaphragm changes as you go, say, across the diaphragm. It will take into account the fact that you might have a brace frame that has an aspect ratio of 1 to 1, right? And you might have a brace frame that's like 1 high and 2 long, right? So now it's a lot stiffer than your brace frame that's shorter. And so it can, as I mentioned earlier in this class, you might have forces that are coming vertically, and then it might hit that rigid diaphragm, a super deep beam, right? It's super stiff. It might pull load out of that frame. Even though if that frame's continuous to the ground level, it might pull it out of that frame and bring it to a brace frame that's even stiffer, like next to it, that you would never capture if you did it by hand, right?
My model.
But a model would capture it, which is beautiful. It's really cool, right? God, it's so cool. I spent days on that because the first project that happened to me on was Miller Dining Hall.
You should.
We had weird shit going on. Yeah, well, it's like it just didn't make any sense. We kept stepping back and being like, this doesn't make any sense. Like looking at reactional forces and like validating, saying, okay, I have my forces that are hitting this building, right? And we distribute those vertically, and so we kind of have story forces understood. And the roof's usually a flexible diaphragm, so you kind of chase those loads. And so in general sense, you have a feeling for the magnitude. But in that case, it was a round building. It was only supported laterally on 1/2 of the basement. You know, it's a clear story basement or open basement on the ground floor. And so you have this huge torsional behavior happening. So we had all sorts of redistribution happening from the top to the bottom of that building. And so, yeah, so you end up spending days being like, what the fuck, scratching your head, thinking like, what's going on? So
Is there ever any instances where you can kind of replicate that with a flexible diaphragm just by over-designing certain elements of it?
Yeah, I mean, in reality, there's no such thing as a flexible diaphragm,
Yeah.
right? Everything is semi-rigid, right? I mean, I don't know if, so in Concrete 2, when I took Concrete 2, Jerry Stevens took a lot of time going over diaphragm design.
Did that too.
Did you? So then you have like truly flexible behavior. You have this continuous beam model approach that you could do, right? You essentially look at, you had 3 frames in series and the diaphragm extending over all 3. That one in the middle you could assume is like a support on a 2-span continuous beam. That's gonna give you a different answer than if it was a simple supported beam, like that would be our flexible diaphragm approach, right? Or then you step a step further and then the code allows you to just do full rigid, right? Assuming that that shit does not displace at all. It's like perfectly infinitely stiff, which gives you different answers still. So I'd argue if you did anything, it should be just modeled. You should just model it. Take the component that gives you the greatest in-plane stiffness. So for a wood diaphragm, it'd be the sheathing, right? You could model that sheathing, whether it's 5/8, 3/4, whether it's the roof or the floor, right? And you could model that, and it would give you a pretty good idea of how that load is distributed. In the end, it's a guess, again, right? Someone could come to you and say, that's bullshit, Madison. You should not have done it that way. That's fucked up. You did it wrong. Right? The people will do that. So then you have to tell them, hey, this is why I did, this is what I did, and this is why I did it. Fuck you, right?
I'll do that.
And you'll find a lot of engineers that'll say, okay, fair enough, right? You gotta be able to convince them, or at least defend yourself. Because it's really just an educated guess. And the code allows you to do rigid diaphragms, right? If your displacement of the diaphragm is less than the overall displacement, okay, or vice versa, then you would have this assumed flexible behavior of your diaphragm, so that it's way more stiff than or way more flexible than your lateral system is. So you could just say, well, hey, the code tells me I can take this little shortcut, right? Or you can nerd out and just design it and put it in VA or RAM and have it do it. Can you do wood diaphragms in RAM? I assume you can, right? Never tried it? Because you're doing it wrong.
I was just messing around with the end releases on like this knee brace frame, weird thing.
Eccentric brace frame?
No, it's just
A knee brace frame.
It's got-
What are you guys doing over at DCI these days?
Justin Timberlake's barn,
Nice.
studio barn. And like there's a purlin supposedly, and then knee brace in the column and the beam, and then same on the other side.
Yeah.
So I was just trying to get like all this is right, make sure that it was doing this properly.
Yeah, I mean, the idea is that based on the connections and how you decide to design it, right? I mean, if they were like tube steel knee braces or something, and you welded them all the way out, like all the way around at the end,
Yeah.
you got a lot of moment like transfer there, right? And I would say you probably should make that fixed. Because if you don't, then you're going to under-design the supporting elements, right? As well as the brace, because now you're saying the brace is not taking as much load as it really would, right? Especially flexion. So, yeah, releases can be a pain in the ass. And then you can go through, I don't know how RAM is, but like in VA, when you start doing that whole thing, well, like in this case, right, we had this column with our 3 beams. If you go through and you released all of these beams around this column, right, unless this column has some sort of restraint with rotation about its axis, then this model becomes unstable and it won't run. And you sit there and you maybe have 350 of these things, right? And you've got all different plates and load cases, and it might take you a long time to even analyze this. It might take 5 or 10 minutes for VA to tell you that it's unstable, sort of thing, right? And so you end up starting to chase this behavior where you over-release it. And we'll talk about that in a second.
Why is that unstable?
Because the column itself can rotate, right? So with
Oh,
respect to,
absolutely no.
with respect to the,
Restraint.
yeah, well, so like, if you looked at it,
Still.
if you had a column, right, that was sitting on the foundation and it ran up, and then at this level you had beams framing transverse, right, in 3 directions, right? If this column wasn't fixed at the base with respect to rotation, VA has no idea, right, in the real world that this isn't going to rotate. to VA, there's a degree of freedom that has no fixity, has no boundary condition, has no nothing. Right? Can't apply forces on it. So then in VA's world, this column can just sit there and spin. Right? And it can't find a solution. The K matrix becomes singular. And so then they can't take the inverse and then it craps out. So you have all of this going on everywhere. So in some cases, like, right, if you had a steel gravity frame, a lot of times all your connections are released with respect to moment, right? You have shear tabs everywhere, sort of thing, right? You have very simple base plate connections for your columns to your foundations. It's just a simple little 3/4 inch bolt, 4 bolts right around the perimeter. You guys have seen those details, right? So you assume it's a pin, it can rotate, right? It takes gravity loads. A lot of times you could grab every member in the model and release all the ends. Right? Well, when you do that, then you start taking these considerations where, right, you might even have a node that gets released to the point where this node can just spin around. Right? There's nothing holding that node. So like in a lot of cases, what you end up doing is, if you want to release all of these, you can release all of them but one, right? Because this node can rotate, for instance, right? So, man, you guys are just, this is a great discussion today. Sick. All right. So what does VA do though in this case when we set things to 0? It rearranges the stiffness matrix, right? The stiffness matrix is a series of column vectors that associate with the forces required to create 0 displacement at that degree of freedom. So we could essentially label our degrees of freedom in our stiffness matrix. So VA takes it and partitions our stiffness matrix something like this, where it reorganizes our stiffness matrix. It shuffles it around, okay? So that we have our degrees of freedom, which are fixed, right, that were non-released, are in one area, and then anything that references back to the released degrees of freedom, right, we move them into our stiffness matrix. So we have, then we look at, right, our degrees of freedom, displacements. We have now degrees of freedom associated with our fixed and released behavior. Then we also have forces, fixed, forces associated with our released degrees of freedom. All right, so we have F is for non-released. Or fixed degrees of freedom. And as you can imagine, our forces, our displacements, and our stiffness is associated with released degrees of freedom. Are you pulling a Brandon today, Simon? Oh, okay. No, I mean, I'm kind of envious of Brandon. He can just sit there. It's beautiful.
Sponging up.
Is he? Are you good? You sponging? You soaking this up?
Right.
Okay. All right. Just making sure. Sponging it up. All right. Well, if we actually multiplied, well, I guess first, when we look at this matrix, right? If we release the moment transfer, or release the translation, right? Any of the forces, the nodal forces that are associated with released degrees of freedom, they have to be 0, right? F sub r must be 0 because no forces at released degrees of freedom, right? Man, I gotta hurry up. We can really just, fuck. So our partitioned equations, I was gonna write all these out. I don't know if I'm going to. I'm going to. Here we go. Become, right? So we just multiply those series of two equations. That's what those are. There's that matrix. We get KFF d sub f plus KFR, right? Those are the fixed degrees of freedom, right? The row versus the column in our stiffness matrix now, times our release degrees of freedom, FF, right? Our fixed forces, or forces associated with fixed degrees of freedom. Our energy equivalent forces on the fixed degrees of freedom, we could call this equation 1. We get KRF dF plus KRR dR. Hope you guys are keeping up. FR plus FER. As I said, FR is equal to 0. This we'll call equation 2. So we solve 2 for dr and sub in 1. 1. Two for dr, and we sub it into 1. We get this equation that VA is all doing in the background. When you release any degree of freedom, it's reorganizing our stiffness matrix for every single element, right? Depending on our fixity, we end up with this equation, F sub F plus FER minus KFR KRR inverse FER. So what do we end up doing? Well, we end up modifying our energy equivalent loads, right? So these are the loads. We know that you can't actually have nodal forces with respect to release degrees of freedom, right? If we say there's no moment transfer, we can't have M1 or M2, right? Depending on what we released. Similarly, now, like you guys are doing in the homework, you have these energy equivalent forces, right? Those are forces that are happening out in the field of our element. Our element doesn't give a shit what's happening out in the field, right? It only cares about what's happening at the nodes. So we have to take those field functions, right, or field loadings, and equate them back into nodal loadings. So what does this do? Well, this takes those field loadings and brings them back to our local, right, our nodal, sorry, not local, but nodal forces, taking into account the fact that we might not have moment transfer now, right? That changes the way that our beam behaves, right? If we can no longer have a moment force at the end of a beam, it's gonna make that beam go from thinking it's fixed, right? Say fixed pinned or something like that, right? So that's gonna change how we would distribute the forces that are acting within our element out to the nodes, right?
What happened to FEF?
FEF?
Yeah, it'd be like FF plus FEF.
FF plus FEF, yes.
But FER is not 0.
So that one's F.
No, this is,
Which ones are K's and which ones are F's?
That's an F.
what are you talking about now?
You just go K, F,
So it goes KFF minus KFR
times KRR.
times KRR to the inverse times KRF times DF equals FF plus FEF. It must be FEF because we're going to modify, we're not going to modify our energy equivalent loads with respect to the fixed degrees of freedom, right? So those aren't going to change. We're really going to change now. We have these energy equivalent loads, right? Regardless, the loads that are acting out in the field. But we need to now modify them and move them to the fixed degrees of freedom, right? Because we cannot have forces in the released degrees of freedom. So that's what this is all doing. So FEF minus KFR times the inverse of KRR times FER. I'll fix that in my notes. So this is our modification to equivalent loads due to release. Wow, cannot spell. Release. As. All right. This whole thing here is our equivalent stiffness for our released element. What do you need, Mike?
Oh, I just couldn't read one of the words.
The equivalent.
Yeah, is that modified?
Modify or modification to equivalent loads due to our releases, right? So we have forces that we would normally have in these degrees of freedom we release, right? We'd have like in the homework, right, you're gonna have a R1, M1, R2, M2. Well, if you say that M1, you cannot transfer moment, it means M1 has to be 0. But when you take our forces that are acting between our nodes and you put them to those degrees of freedom, well, we still have those loads, right? Well, now we need to take those loads and move them into our fixed degrees of freedom, and so we modify them. So that's what this is going on. This one is saying, well, now, instead of having this case where we have fixity, right? We have a moment, we have a reaction at the end, right? We might not have the ability to have that moment, so the stiffness of our element changes, right? It's no longer the same stiffness, because now it can rotate, right? We go from a fixed, right, to maybe a fixed pin, or something like that. Or it might be a fixed, it might be just like a cantilever, right? Where it can have the moment and forces on one end, and it can't have any moment or reaction on the other end. So we get this K equivalent. So VA does all this in the background, right? Once it has this K equivalent, right? This K equivalent has essentially terms in it that you then pull out, and we would fill a stiffness matrix back. We're going to refill the element stiffness matrix, right? So we had 3 degrees of freedom at each node, so you have a 6x6 stiffness matrix. So you end up taking these values, right? We essentially now have an equivalent stiffness matrix that only has values attached to the degrees of freedom that are fixed, right? Because if you have no ability to move forces, your stiffness is 0, right? You can't have any ability to resist force, right? So your stiffness is 0. And it's 9:50 and I lost time. Damn. We need to get through this. I will post the notes for elasticity. We'll have to finish just a little bit here.
We're just too good at discussion.
You are too good at discussion. I thought it was great. Hopefully you guys got some value out of it. I love that shit. Okay? That's what the rest of this class is going to be about, hopefully. Okay? If I can walk you guys along, get you there. Okay. Homework due next week, okay? And I think that's about it. Probably, maybe next week. I don't know though, I don't know.
If you just give it to us early enough to finish it before.
Yeah, if I do,
Like,
it'll be due after, I'll make it due after spring break. It's probably gonna be attached to elasticity elements and have you guys do a little bit of stuff. I don't know, but I also thought, well, I could also just take that and plug it into the midterm and have that be a problem in the midterm.
Don't give us a
No, I
midterm
mean,
question.
it's not. You got a lot of options. You got a lot of options.
Don't give us midterm questions if we haven't had a homework on it.
Why not?
That's usually a pretty standard thing, like you don't test and just like do response.
Why?
Sometimes because you've only learned it and then like,
I mean, I can't, like, that's not true.
Yeah.
That's not true.
Any other professor, I put stuff on note, on exams that I haven't done a homework.
That's not true. Like in 315, I will test on stuff that I never explicitly did in class. Like we talked about it, and they probably had a homework on, say, beams.
How did they do on those questions on the exam?
You did all right. I mean, in the real world.